Hello everyone. Our project is titled Fast Online Search and Retrieve using Learned Spatial Arrangements of Common Objects. So let's break that down. Imagine a messy but structured environment, such as a kitchen. In your kitchen, you have your shelves, your cupboards, and your counters, and oftentimes people will store the items in their kitchen in an organized way. For example, I might like to have my condiments on my shelves and my cups on my counters. So maybe this information could be useful for us. Imagine the following situation. It's Kevin's turn to make dinner again, and his food's awfully unseasoned. So maybe my robot can help me find my hot sauce. So the robot might know from past experience that the hot sauce is usually on a shelf, which is usually above the sink, and can use these associations to search for and retrieve my hot sauce. The robot doesn't know where the sink or the hot sauce or any of the items are just yet, but it knows that if it sees the sink or the shelf, then it must be close to the hot sauce, and will guide its search in that direction.
Okay, so let's talk a little bit about our approach. So given that we have associations between objects, but we don't initially know the locations of any of the objects in the scene, the question is, how might we search for a target object? And so the first thing that we can do is we can partition our space into a 3D grid of cells. And then from here, we can run a few standard algorithms. So for example, one of our initial ideas was to formulate a graph search problem, where basically each of the grid cells is a node in the graph. And we could use an algorithm like A star to search over the space and use our associations as a heuristic to guide the search. However, we decided not to pursue this algorithm because in order to explore the nodes in the graph, the robot needs to physically visit the corresponding locations in 3D space, which can be quite expensive. And so instead, we decided to go for a grid search algorithm. So the way that the algorithm works is that we essentially define a belief, which is a probability value, which we associate with every cell in the grid. And it defines the probability, given the robot's current knowledge of the scene, the probability that the target object is located in that grid cell. And so what our robot does is until the target is found, it will choose a cell to move to and observe using IK and RRT, and then it will make an observation and then update the belief. So for example, if the robot sees an associated object, it will increase the belief values, and if the robot sees an object that is unassociated or it sees empty cells, it will decrease the belief values at those locations. So how do we actually solve for these associations? Well, in our project, we consider them to be 0, 1 values for every values ranging from 0 to 1 for every pair of objects in the scene. And so, for example, at a high level, the way we collect this data is we simply sample a bunch of views, and we basically collect data as to which objects are located near each other.
Our experiments are as follows. We run our search in a complex environment with many bins and shelves where certain items can be located randomly with higher or lower probability. Additionally, there are some walls that obstruct some views. We compare our approach with random search as well as grid-based search without associations, which also collects information about the scene but cannot leverage associations to guide a search.
All right, so here's our setup in action. A robot tries to find a can of tomato soup among all the clutter, and the only perception it has is a camera attached to its end effector. Before we arrived at our cool solution with associations, we tried both random search and grid search without associations. As you can see, random search fails to converge on a good strategy and essentially makes arbitrary movements. And the grid search without associations, while it does better, it doesn't have any knowledge about the spatial arrangement of objects. So we have to expect it to search the entire space before it can find the solution. By contrast, here's our method with grid search and associations. On the left, you can see visualizations of our belief space as 3D plots. And if we play the video, you can see the robot first move into a neutral position before looking to the top of the scene, where it catches a glimpse of the cupboard, which is tightly associated with the tomato soup, so it goes to investigate the cupboard. It performs a few other actions before finally realizing that the tomato soup is at the bottom of the cupboard, where it currently finds the solution. Along the way, we encountered several unexpected technical challenges. For example, IK's gaze constraint did not come out of the box accounting for occlusion, so we had to attach a cylinder to the end of the end effector to ensure we have direct line of sight with our target. Regarding the algorithm, we observed several problems in the initial stages of testing that we tried to address using the following 3 measures. First, to account for the trade-off between runtime and resolution, we adjusted the grid size of our discretization. To avoid nonsensical actions, we adjusted the belief space prior, and to prevent weak association propagation, to avoid having our beliefs explode and vanish, we had to modify our update rule. To make such a system more useful in the real world, we'd first like to investigate moving occluding objects out of the way by some kind of online interaction, and of course, to make sure to test and learn over more environments. That wraps up our presentation. Thank you for watching.